Thank you very much for the invitation. Physics was mentioned a couple of times by now. Economics is of course not physics. Some economists are making very clear and very sure that economics is a social science, studying the production, distribution, consumption of goods and services, etc. But what I would like to argue is that one could take a little bit more of an atomistic point of view than we are usually looking at the economy. And maybe, yeah, that's the thing I would like to do. What could we do by taking a much deeper look and adding, so to say, to the Kepler mode, to the Newton mode, the quantum mechanics mode. Physics made lots of progress by accepting atoms 120 years ago. There was a turning point in physics. So what would be the atoms of the economy? It's the firms. Why the firms? Why not the products? Why not the people? Why not the industry sectors? At the firm level, most decisions are made. That's central point. At the firm level, you decide what to produce, how much you produce, what prices you set, who you buy from, who you sell to. All the basic decisions, or almost all basic decisions, are taken on a firm level. Would also like to make the point that these atoms are not yet an economy. What you need for talking about an economy, you need at least 3 ingredients. One is you should know the supply chain network. Then you need to know how are these nodes, firms operating, what are they doing, how are they taking inputs in and outputs out. You need to know the production functions, and you third and maybe most important, that makes the whole thing a complex system at the end, is that you have to know how firms relink themselves within this network, how the system changes. If you have never seen an economy, no, here is an economy. Here's a picture of an economy. This is the supply chain of Hungary at over 1 month of existence. What you see is 200,000 companies. These are the green dots, and about 1 million supply links. These are the links you see. At this stage, yeah, that's an economy, does not help us anything. But if you zoom in, you immediately see one important thing. So we take out 500 of these firms. Every firm is a dot. Every supply link is an arrow. And you immediately see that you see a couple of chains, but this is not a supply chain. This is a network. This is exactly of the type what Simon Levin has been talking about. And through this network type of structure that links not every firm with every firm, but many firms in very specific ways, this is the origin of why the economy is efficient, why it's robust, why it's resilient, but to what degree? And this science can help us to figure out. So the second ingredient that we need is we have to assign a production function to every company. And what is a production function? A production function, I've shown on the right part here, part of this network. Look at firm number 6. It takes a couple of inputs, 3 inputs, and produces one output that it sells to company number 8. The production function is just which inputs firm number 6 takes and how much, and what recipe it needs to produce its output 8. When firms, what are these production functions? What do these production functions look like? There's different types of production functions. There's linear and non-linear production functions. The Leontief production function is something like a recipe for cooking, for baking a cake or something. You need inputs to certain ratios to produce one cake. Linear production functions is something like a retail company. You buy shirts and trousers, and you sell shirts and trousers. These inputs don't influence each other too much, so you can superimpose them in this linear production function. Or something in between is a Cobb-Douglas production function. That is a linear production function in logarithmic units. Don't take that too seriously. What we are doing is to assign a production function to every of these 200,000 companies, or to every company in an economy, by estimating the parameters of this generalized production function that you can see here. I don't bore you with this. This is done with machine learning techniques and combining different data sets. And the third component is how do firms rewire? If I've shown you this image of the Hungarian economy. This is a snapshot. Within 1 year, the picture will change radically. 10% of all the companies that you have seen here will not exist in the next year, and of course, all the links that you have seen are subject to change. How do companies rewire in that system? How do companies change their suppliers? How do they change their customers? That's an important question. If you have time-resolved data, you can learn this company by company. You're making errors here. You have to estimate how this is done, but this can be done. And for what I'm going to show in the next slides, we are assuming a very, very simple rewiring mechanism. And this rewiring mechanism says that companies or firms with a high market share are hard to replace. So we are looking at the market share. If the market share of a company is high, then if that company goes out of business, it's very hard to find a substitution for that. And if a company does not find a substitute for a company that went out of business, it, according to its production function, has to change its output. So we are putting all of this together into a simulation environment that allows us to model the economy one-to-one. We can do an agent-based model where we represent every company in an economy, and including every buyer-supplier relation. How do we get these buyer and supplier relations? There's different ways of doing that. You can trace payment flows. So or you can look at value-added tax payments. So payment flows could be monitored by banks, consortia of banks, tax payments is available to authorities, financial authorities, or central banks. So what can we now do better with a one-to-one model of the economy? So note, we no longer have to aggregate things. Economics is kind of, or has been kind of, an art of aggregating many actors into representative agents which could be dealt with. If we have a one-to-one image of the economy, we could do many things a little bit better. For example, we could do better input-output analysis. We don't have to focus on sectors, industry sectors anymore. We can look at the firm level. We can identify the weak points of economies. We can compute the systemic risk of individual companies that Simon was pointing to. We can give numbers to companies and tell how much risk they bring into the economy. We can do much better growth predictions. Why better growth predictions? Because we see the geometry of the whole thing. We have yesterday heard that geometry plays a big role in physics. If you want to do physics, you better know what your geometry is. What is the geometry here? It's this co-evolving network. This is a space that restricts your possibilities tremendously. If you have these constraints, you can do better predictions. For example, you could look for the origin of inflation right now that's haunting Europe and the United States. We can quantify efficiency. We can look where is it working efficiently, where is it not working efficiently. We can talk about the optimality of resource allocation. We can do classic questions of economics. We can look and monitor how the green transition is taking place. We see how economic activity is shifting, reshaping over time. We can compute and monitor the carbon usage of every firm. It was mentioned yesterday a couple of times this session that it would be nice to know who is burning how much carbon in order to compute and figure out how many kilograms of CO2 is in every product that we sell. We could base a new tax system on this, a smart carbon tax system, not just taxing it, but taxing it in a way that supply chains would reconfigure and reshape in an ideal and optimal way. We could talk about the potentials of circular economy. Why? Because we see which flows are circular and which products end up in a dump. We can link all of these to labor economics and also to what Brian Arthur just said, to complexity economics. We see new technologies evolving, and we can make movies of what Brian just said. So I'll give you a couple of examples of what we can now do. How can we quantify the resilience of an economy? Everyone is talking about it. What is resilience in numbers? So we want one number. We call it the Economic Systemic Risk Index, ESRI. It quantifies how much does the total production of an economy go down if I would kick out that particular company. That's the systemic risk, or the economic relevance of a company. You have to compute this index upstream the supply chain and downstream the supply chain in different ways. I don't bore you with the details. It's a formula which needs other formulas to compute. If we compute this systemic relevance, this economic systemic risk index for every of the 100,000s of companies in Hungary, you see a beautiful power law, which people from complex systems always like. But you also see, so power laws tell you that outliers are tremendously important. Outliers dominate the scene. It's very different from Gaussian statistics. But what you see here, that this systemic risk in an economy has outliers of outliers. Couple of companies that carry tremendously large systemic risk. That's a sign that the economy is not like physics, a homogeneous isotropic thing. It's a highly heterogeneous object where the details of connections tremendously matter. So this is now the economic systemic risk index on the left-hand side. Tells you that there's about 25 companies in Hungary. If you take out one of these, the total production of the country would go down by 23, something like this, %. So tremendous disaster. This is, of course, this includes, of course, the big car companies, the atomic power plant, etc., but also a number of very small firms where you would never think this would happen. But a small firm's product would kick out, would be able to kick out a large company. We have done an exercise to reconstruct, to go even one level down to a product level, to construct a supply chain network of pork production in Austria, including 40,000 companies and hundreds of thousands of links. And once you have such a time-resolved image of an economy or a part of the economy, you can do monitors in completely different way than you do it today. So here we have a part of Austria. You can click on every producer in the supply chain of pork and see what happens if you kick out that producer. That brings down the total availability of pork by this and that %. And here we list every supermarket it's a long list, every supermarket in the country, and see by how much pork would be less available. So this is a new kind of planning that could become valuable for the next crisis to manage. Maybe, yeah, I just said, we can compute financial risks that Simon Levin pointed to in a completely new way. If we have on this layer the supply chain, if something happens to company F, it will no longer be able to repay its loan. It's a banking system up there. But if F fails, D might fail, and then D will no longer repay its loans. So here we have the connection to of the real economy to the financial economy. In Hungary, we are in the lucky position to have the data. We have the firm credits and can compute the financial systemic risk that affects, again, about 20 companies very, very strongly. So if we look what that means, if we're looking at financial risk measures like the expected loss or the expected shortfall or the variance at risk, these quantities, if you add the supply chain to the picture, the real economy to the picture, the underlying distribution functions change tremendously, amplifying the risk by 100, 200, 300, 400%. So we have a clear misperception of financial risks if we don't take the details of supply chains in the real economy into account. And maybe a last example in the last minute. How could we use this new atomistic knowledge about the economy for planning for the green transition, for example? Imagine, yesterday it was mentioned that such a thing would never be done by a politician who is clear in his mind or her mind. Make a statement like, next year we have to reduce CO2 emissions by X%. No one is doing that. How would one do that? You would have to incentivize companies to reduce emissions. You would have to incentivize them very strongly to reach such a goal. And the strongest way of incentivization is, of course, to close them down. I'm not suggesting to do that, but just as a thought experiment, let's ask the question: which companies do I have to close down to reach 20% reduction of CO2? So that causes social stress as soon as you start closing down companies. It causes social stress. How much social stress does that cause? That's the number I computed before. It's the economic systemic risk index in the units of jobs, for example. Yeah, you can compute the ESRI in units of employees lost if a certain company goes out of business. So I can plot the emissions of, this is the 200 most important companies in Hungary. We plot the emissions on the y-axis and on the social stress or the economic systemic risk and the index on the x-axis. We see that there's companies that have relatively large emissions and would cause lots of social stress if you close them down. But there's many companies that have large emissions and have no social relevance. These maybe you could close down first. So if we order the companies with respect to CO2 emissions per stress caused, here's a recipe for closing them down. And here's a comparison. It's a little bit hard to read, but the red curve is the CO2 emissions savings as we are closing down companies. If we do it in this optimal strategy, we have to close down to reach our goal of 20% reduction of CO2 emissions. We have to close down about 60 companies. We save 25% of emissions and increase jobless rates by, I don't know, 5%, something like this. If we would do an obvious alternative, that we shut down the biggest emitters first, the red curve is again the emission savings, is very efficient in emission saving. There's no other better strategy, but immediately you reach huge numbers of jobless rates. So we reach our goal for the emissions after closing down 10 companies, but we have already 30%, 25% of jobless rates, which is undoable. So again, details matter, and we can. It's not a realistic example, but it's just to show you how planning could work. We could test strategies for thousands of different purposes. This is just one thing to, yeah. So what I've shown you is a very technocratic point of view. This is not what economics usually is. Reality will always be different. If you compute the systemic risk indices, yes, but if the real crisis happens, it will be different. Why? Because the human component enters. We have psychology playing politics, playing interventions. We have risk management in place, etc. So I think an obvious thing would be to try to come to a symbiosis, a rethinking of economics together with economists and complexity scientists, network scientists, statisticians, and I leave it with that. Thank you.